This is possibly one of the hardest parts. So I'm going to take it fairly slowly, and it's important that you interrupt me when I skip over something. And it is also fairly abstract in that we're working not on specific examples all that much, although there will be several specific examples. And I will try to connect it to the elevator project as much as possible wherever it is possible. But we are following a logical chain of how do we make a distributed system that works within the context of a reliable system. And so there are a lot of, like the lecture is structured as just a sequence of logical arguments for this is why it has to be the way it is. And these are our design parameter constraints. Not so much as like this is what it is and how it could be, but like this is how it must be because we are constrained very much in our problem space. Oh yeah, tangents. Let's do tangents first. As not so much a tangent, but just like a recap from last week, just to make sure everybody gets it, because there is a chance, of course, that some people, at least I got some questions on the lab last week, which means that not everybody quite captured the essence here. The point was that failure is a given. The things we are making are going to fail at some point to some degree. But of course, they can't fail because if they fail, they don't work anymore. So we need to make them not fail. And the only valid solution to something crashing or something being disconnected or something like that is to either take over or to try again. So try again locally or try again by somebody else doing it instead. And that somebody else doing it instead part, that's the distributed systems part. So yes, they are connected. So on a single node, that means restart. And of those two, or of restarting, there are really two ways to do it. One is to try everything again. And you can, as we did with process pairs, optionally also restore from a checkpoint so you don't lose any progress. Or the other alternative is to try only the things that failed again, and then also, again, optionally undo something. And if you are going to undo something, you use goto and scope guards and so on. Here is the important part. The important part aren't the optional parts. Those are the hard parts. But those aren't the important parts. The important parts is that these optional things can fail too, right? So the undoing steps can crash, or you can crash while undoing, and you can crash while restoring from a checkpoint, or your checkpoint could be bad, or your undos could be partial. So just beware of that. That's probably the most important part, is that these optional parts are optional for a reason, and that reason is that they can fail. So the only reasonable solution to things failing is that, the big problem that you need to solve is that everything can fail at any time for any reason. And thinking, oh yeah, let's just try this one small part again and just try undoing a small part. Since that can fail too, it's not necessarily a good solution. Yes, drastic measures are drastic, but they may be necessary. And as I said on the previous slide, that's how you do it on a single node. Like on a single node, we try our best to restart, but sometimes it can't restart because it's dead, Jim. So we compensate for failure by having redundancy. All right, so the system as a whole needs to work even if a single part of it does not. And the only way to really solve that is with physical distribution. Because if you're trying again, if you're disconnected, trying again doesn't help you connect, right? The cable is cut, you can't uncut the cable with software. So the only solution there is to take over, and that is really the foundation for the elevator project. Is if it crashes or if it gets disconnected, you need to be able to take over. And in order to take over, you need the information of what to take over. In order to get that information, well, you need some kind of distribution, you need some kind of communication. The problem is, of course, that the communication part can also fail. So if the nodes can fail and the communication between the nodes can fail, how can you offer any kind of service guarantee if everything can fail, including the communication? So that's the hard part. So yeah, messages can be lost and reordered. We need resending of some kind, because if we lose a message, well, we're going to get to it, but if we lose a message, then presumably the message had content. And if the message has content, presumably it was important. And if it was important, then losing it is kind of a big deal. So losing it is not, again, it's going to happen, but it's not an option. Was there a bottom line here? Yeah, there's a bottom line. So we can just resend everything all the time without any kind of structure to it, but the goal for today is to figure out what exactly is that structure. Like, how do we solve this problem of nodes being able to fail at any time and the communication between the nodes being able to fail at any time for any reason in any manner of different ways? How do we solve this in such a way that the output of the system is still correct, even though everything going on in between inside the system is potentially wrong? So how do we make a reliable system? The system outputs are reliable, even though the parts that we're making the system out of are unreliable. So that's the preamble for today. Let's talk about intermediates. As I said, the only thing that really matters is the final output. All of the things in the middle, they do not. Let's think about that. So we divide our system into several different tasks. These are the threads. So again, we're pulling a third thing from our back pocket here. So this is what we do. This is how we program in this course, at least. We divide our program into multiple different processes. Exactly how we do this and what the divide is, we're going to get back to that in a later lecture. But the idea is you have a thing that needs to be done, and a thing that needs to be done is an output that needs to be set, or some content that needs to be generated. So if you have some output, it means you need to have to make it, and in order to make it, you need something that can make it. And the thing that can make it is a thread, because threads do something. Functions do not. In order to have a process that is meaningful, of course, it needs to have inputs, it needs to have outputs, and it needs to have state. Let's see what happens if we cut out one of these things. Do we still have a meaningful process? So if we have a process with no outputs, it doesn't do anything. So think about it. We have a thread that only takes inputs, but it doesn't make anything, which means that it can't have any interactions with the outside world. If it has no effect on the world, then it has no effect, so we can just delete it. So a process with no outputs is not a valid process. If a process has no inputs, it means that it's predictable. Do you see this? It has no inputs, so it will always generate the same thing because it can never change, because it is never affected by the outside world. If you have a process that always does the same thing, then of course it's predictable. And if we have a predictable process, then it doesn't really need to be a separate process, because it always does the same thing. If it always does the same thing, we can just do it ourselves. And if we can just do it ourselves, we can integrate this into a real process instead. So a process with no inputs is also not a real process. And then what happens if we have a process with no state? Well, the only thing that a process can do if it has no state is to map the inputs directly over to the outputs. And a direct mapping from inputs to outputs, that is just a function. Do you see this one as well? If we have a thread that doesn't remember anything, it has permanent amnesia, it always just calculates the outputs based directly on the inputs. And something that calculates the outputs based directly on the inputs, that is what a function is. So in this case, no memory of the world, it is just a function. So in order to make a thread that does something useful, or in order to make a process that does something useful, it needs to have inputs, it needs to have outputs, and it needs to have states. If it is missing one of these three things, it is not a process, fundamentally. Do you see this? Yes?
I just want to ask what the state of the process is.
State is just any local data, any variables that it saves locally. So when you're making your Go routines on the first exercise, you're making your number server, the I variable, that is a local state. If it doesn't have that I variable and it cannot increment or decrement anything and it has nothing to do, then it is not a process. So we get these two statements as a conclusion from our observations about processes. A process without state is not a useful process. It needs state in order to be useful. And in order to in order for the inputs or the outputs to be useful, they need to be not the same thing all the time. And nothing is, of course, the same thing all the time, so removing them entirely is, as we could see, makes things not a process anymore. A process with no outputs is not a process. A process with no inputs is not a process. But a process that always does exactly the same thing as its output all the time is also not a process. And a process that always receives the same thing as an input every time is also not a process. So these messages have to be unpredictable in order for them to be useful. Do you see this as well? Can I get like a slight affirmative nod from those who are like, yes, good. It is important that we follow these steps, because if you fall off at any point, the conclusion at the end of the lecture does not make any sense at all. Right? Now here is the problem. Do you see the problem? The messages have to be unpredictable to be useful. We are sending messages on the network. Messages on the network will be lost and reordered. That too is unpredictable. Now we have two layers of unpredictability here. We have the desired unpredictability, which is necessary for the functionality of the process, and we have the undesirable unpredictability of the reordering on the network. So our tasks need messages. It needs unpredictable messages in the predictable correct order. So our messages contain two pieces of information. First is the obvious parts, the message content, the payload. What are you sending? If the message has content, it implies that the sender is something it considers useful for you. And then the second part is the fact that the message exists. This one is less intuitive, but it implies that the sender exists and it was recently doing something. And since it was doing something, what it was doing was also considered to be useful. The messages are the inputs and the outputs of the processes. Right? Now here's the logic chain. You should be able to follow this. If the inputs and the outputs are necessary to transform state, right? We need unpredictable inputs to transform our state, our local data. And we need correct local data in order to perform useful work. Then the inputs of the process are necessary to perform useful work. Right? Makes sense? A state machine that just gets random inputs as its inputs will not be able to produce any kind of useful output. Does that make sense? Right? Captain Obvious strikes again, right? We get random stuff in, random stuff out. Garbage in, garbage out. So we need to get not garbage in. But we still have this problem with messages on the network can be arbitrarily reordered. Right? So we can lose messages on the network. We can get reordered messages on the network, and the content of the message is unpredictable. How do we solve this problem? If we lose a message, it is in some sense equivalent to losing the transformation to the next state. Right? We cannot, in a state machine, go to the next state if we don't have any events that come in. If we don't receive that message, it will have consequences for what the process does. Are you with me so far? If we reorder the messages as they come in, we reorder the events to our state machine, it will scramble the internal states. If we get things in a different order, a state machine will sometimes do different things. That's the entire point of a state machine. So if we scramble the input order, we will scramble the output order. If we scramble the output order, we may get the incorrect functionality. If we duplicate messages, we might duplicate the outputs. So we get an input, it produces an output. We get the same input again, it produces the same output again. That might be incorrect. So the problem we need to solve is this ordering of the inputs. We need some way, we need the messages to arrive, and we need the message content to be intact when it arrives. but we also need to be able to receive messages that are in any order. So the content of the message cannot just be what do we want to have arrive on the other side. The content of the message must also include something about the order. And when we are receiving messages, we cannot just blindly accept anything that comes from the outside world. We also have to take into account the order. This is the problem to solve with distributed systems. How do we make our program produce the correct output, regardless of what happens in the middle? Our output is something that happens to the external world. Our input is something that we get from the external world. The network communication that we have between our nodes is entirely up to us and is unobservable from the outside world. How do we make a system that compensates for the unreliability of the network by communicating on the network? How do we make it reliable with an unreliable part? You with me so far? Did I lose anyone? Okay, good. As an aside, or a slight aside, this is not, slight tangent. How do we solve message loss? Like, how do we solve losing a message? What is the one solution to losing a message? Well, it is to send it again. The message content is useful, so we need to send it again. So let's see if we can get rid of the message loss problem. The only way to deal with the message being lost is to resend it. And when we're resending, there are three main ways to resend. One is to just send everything periodically, and the resending is implicit. So if you're sending something periodically and one of them gets lost on the way, then the next one will arrive, probably. The other is to wait for some kind of explicit acknowledgement, and if you don't get any confirmation that the message was received, you send again explicitly. This might be more intuitive in some situations, but it is functionally the same thing. And then there is the fourth way. No, not the fourth way, the third way. Do you see what the third way is? What is the third way to resend? Either it's sent periodically or it is sent explicitly when you don't receive an acknowledgement. What is the third way? Hint, it's a trick question. All right, the solution is to do nothing. Your system is interacting with the outside world. And if our system is interacting with the outside world, there is probably someone on the outside who sees that nothing happens and tries again. So that may be an option. So if the user of your elevator sees, oh, the light in the button didn't turn on, it goes, well, clearly I just didn't push hard enough. Right? So here's an engineering hot tip of the day. If you are ever faced with a problem, see if you can avoid the problem. Right. But back to message loss. Resending is not that hard. And resending is also the only solution to losing messages. So message loss is not really a problem because we need to resend anyway. And if we're resending, we get different problems instead. We get the duplication problem and we get the reordering problem. So we've gotten rid of message loss as a thing. We only need to consider duplication and reordering. How good is your math, by the way? Okay. Have you heard about these two things? You've heard about commutative. Plus is commutative, right? So 1 plus 2 plus 3 is the same as 3 plus 1 plus 2. So the order of operations does not matter. If you have something where the order of operations has no effect, then reordering, it doesn't matter. Make sense? And if you have something which is idempotent, it means that getting the same thing over and over again doesn't matter. So for example, the maximum is an idempotent operation. All right, so the maximum of 3, 5, 5, 5, 5, 5, and 5 is the same as the maximum of 3 and 5. So if we are able to make our system have these two desirable traits, then we are able to deal with duplication and reordering without any issues. If we're able to deal with duplication and reordering without any issues, we're able to deal with message loss without any problems. Because then we can just resend. Periodically, preferably. So I am going to focus here, for now at least, on periodic resending. Or periodic sending, really. Because it makes things, I would argue it makes things simpler, but it doesn't necessarily make things easier. Because it's kind of hard to wrap your mind around that things are happening periodically. But of course, the systems we are making are going to be loops. We are making things that run forever, and if they're running forever, they're doing the same thing all the time. If they're doing the same thing all the time, they're doing something periodically. So that's why it's simpler. We're making things that run forever anyway, so why not just do things forever? Right, so back to our main thread here. Our system is embedded, right? The only thing that matters in our system are the inputs and the outputs to the outside world. We can do whatever we want with the intermediates. On the intermediate side, we have, do I mention this on this slide? We have two things, right? We have the communication that we're performing between the nodes, and we have our internal data structures, which are unobservable to the outside world. So both of these are unobservable. So we have the communication part. That's unobservable from the outside world. We're not leaking messages to the outside world unless somebody's sniffing, but that's not intended behavior, so you don't really care about it. And we have the data representation. Again, unless somebody is hacking our system and reading the memory, does it matter? No, of course not. We're not really concerned about that, but the internal state is not observable because it's not part of our outputs. The outputs of our system doesn't care if we use a list or a hash map. It doesn't matter. Do you see the problem? One part of these intermediates. Yeah, we can do whatever we want with it, but so can the outside world. On the network side, the environment can do whatever it wants with the messages on the network. So if the environment can fuck with our messages, but we can also do whatever we want with them, we are limited here in our ability to just use the network to fix this problem. So we cannot solve this problem with the network alone, because the network can do whatever it wants with the things that we use the network for, which means that we only have one option left. The only place to compensate for an unreliable network is to do something with data. We need to store something. I think this might be intuitive for you. In order to know what order something arrives in, you need to remember what you received previously. In order to remember what you received previously, you need to store it in some data structure somewhere. So I think that is fairly intuitive. Are you with me so far? Did I lose anyone? Good. The question is then, on the data side, what exactly do we need to remember, and what is this something that needs to be stored? Something needs to be stored, but what exactly is it? Okay, let's get a so far in here. So far, the messages on the network can be arbitrarily ordered. The system outputs need to be correct. The network outputs, or the network messages, are not the outputs of our system. So we can still keep the outputs of the system correct despite the network being all kinds of fucky. The only way to manage this problem is to work with the intermediates. Of our intermediates, the two things that we can do are send different things or send more things on the network, knowing that it will be reordered. Or we can use some kind of state, some kind of data, some kind of memory of something to deal with what we receive. So we use the knowledge of what we have received previously to impose some kind of ordering on what we receive in the future. The question is, what do we save? What do we mean by ordering, and how do we impose it? And while we know from the desirable traits that we need something that is capable of dealing with duplicate messages because we need to resend, and we need something that is capable to deal with reordered messages because that will happen. So we know that we will be dealing at some point to some level with idempotency and commutativity. With me so far? This is fairly abstract. Okay, so that was branch 1 of our entry point. Now we go to branch 2 of our entry point. So prepare for a context switch here. Let's talk about the cap theorem. Who here has heard about this at all? Good. Then you will learn something new today as well. Okay. The cap theorem states that you can only have two of the three things: consistency, availability, and partition tolerance. What do we mean by these three, and why can we only have two of them? Let's keep going. Consistency means that all of the nodes produce the same output. So what does it mean for them to produce the same output? It means that they have the same data stored internally. In order to produce the same output, they need to know what that output should be. In order to know what that output should be, it needs to be data. In order for it to be data, it needs to be stored. Availability means that the nodes produce output at all. So it doesn't necessarily have to be the most recent output. It doesn't necessarily have to be the output that all of the other nodes would have produced, but it produces something. And partition tolerance means that the system tolerates an arbitrary amount of message loss between the nodes, which includes disconnects. So partition tolerance, it works, or the system keeps working even though it is disconnected. There is a full-on mathematical proof that states that you can only have two of these three. But, you know, let's just not do that and instead do an informal proof. If we want, say, availability and partition tolerance. Oops. This means that the nodes have to produce outputs despite being disconnected. If our nodes have to produce some outputs, but there is a disconnect between the nodes can't communicate. If the nodes can't communicate, they can't share data. Or at least they can't be up to date on what the other nodes know about because they are disconnected. So the only way to make the node produce some output in this scenario is to deal with the outputs being different. Since we don't know about the other nodes, we can't stay updated with them. We can't stay updated with them, we will produce a different output from the other nodes. So it will be not consistent. Are you with me? All right, good. Let's say instead we want availability and consistency. This means that the nodes have to produce some outputs, that's the availability parts, and it has to be the same output. And in order for it to be the same output, they need to communicate with each other. And since they have to communicate with each other, they cannot be disconnected. You cannot communicate with a disconnected node. So in this case, if we want them to produce output and we want them to produce the same output, that is only possible as long as it is not disconnected. Now do note that this will be most of the time. Most of the time you are not disconnected, which means that you can produce the same output on all the nodes at the same time and actually produce it within a reasonable time frame. But the moment you start losing packets and the moment you start disconnecting for real, then you have to sacrifice either availability or consistency. So let's think about it. Let's see the final one. We want consistency and partition tolerance. So we want them now to agree on the same output despite being disconnected. Well, if they're disconnected, they can't communicate, but in order to produce the same output, they need to communicate. So what's our only option here? Well, is wait for the disconnect to go away. So we need to wait for them to reconnect so that we can be sure that they all agree on the same output. And if we're waiting around, they're not producing output. And if they're not producing output, they are not available. Did you follow this informal proof? Good. Question?
If the nodes were to have some kind of state before the disconnect, could they still produce outputs based on that last state, therefore kind of be available?
Yeah, so the question is, if the nodes have a memory of the last thing that they saw, yes, and then they were disconnected, can they still produce an output? Yes, they can still produce an output based on the last thing they saw. But the moment any one of those nodes sees something new that they desire to communicate on the network, and they actually store it and start producing a different output, then you lose the consistency. Or they see something from the outside world and refuse to output something new, in which case you are sacrificing availability. You see this now? Yeah. Okay, so in our system, we need to sacrifice one of these three, or in the situation where we have a disconnect, we need to sacrifice one of the two, of availability or consistency. And we know that we cannot not sacrifice partition tolerance because we will have disconnects. And we also know that we cannot not sacrifice availability. So, well, we need the partition tolerance because we will have disconnects. Nodes will crash and they will disconnect. So on the elevator system, that would be thinking like, no orders are lost despite losing an elevator. We need the availability because we are making the system that needs to keep working despite crashes and disconnects. So it needs to still produce outputs. Outputs in this case is it still needs to run around and serve orders. Our elevator system still needs to do something. It still needs to move the elevator up and down. Sometimes we can get away with no availability. So according to the specification, you can refuse to light up a button after a button press. Right? We weren't able to contact the other nodes, so we're not going to turn on the light in the button, but you need to try again when the user presses again, and it needs to happen eventually. But in a small time frame of a single button press, you can refuse to turn on the button light. But for other things, you cannot do it like this. You cannot refuse to move an elevator after the light is turned on. After the light is turned on, you have offered a service guarantee, and once you have offered a service guarantee, then the elevator has to move. If the elevator has to move, you need to set the motor output. And you can't refuse to set the motor output. So we need partition tolerance, we need availability, at least for some parts. And we also want consistency. It is nice if we have the same data representation on all the different nodes, because then they all know about all of the orders in the system. And you want all the elevators to know about all the orders in the system. Because if you lose something, well, now you've lost an order. So how do we deal with this? But there are, again, some cases where you don't need consistency. For example, you just need some elevator to take an order. You don't need exactly one elevator to take an order. So if two of them show up because something was inconsistent in our system, that's fine. It's not optimal, but it's fine. But there are some times where you do need some amount of consistency. So, oh yeah, and also some other kind of inconsistency that is acceptable is that as long as one button light turns on, you've offered a service guarantee. They don't all need to turn on. And then the question is it okay to move an elevator even if no lights turn on? And according to the specification, it's allowed. During exceptional circumstances of high packet loss, this is permissible. When you have no packet loss, it is not permissible, but when you do have packet loss, it is permissible. So that is an acceptable inconsistency. So there are some acceptable unavailabilities. There is actually only one, which is the one that is noted here. But there are some acceptable inconsistencies in our code. So let's do our so far slide and then take a break after it. Huh? So far, we have to manage the arbitrary time ordering, our duplicates and our reorders on the network by using our freedom to do whatever we want with the intermediates. The two intermediates we have are, we can send whatever we want on the network, knowing that it will be reordered, or we need to save some data so that we know about, we know what to do with the things that we receive in the future. We have to sacrifice consistency to achieve availability and partition tolerance. And we need the partition tolerance because the system needs to work even though someone is disconnected. And we need the availability because the system needs to keep working. We also want to constrain the inconsistency in our system. We don't want our system to just produce random garbage as its output. Yeah, it's producing output, but the elevators are going random places. That's not correct. We still want to constrain the inconsistency so that it is at least as correct as it has to be. So we can constrain the inconsistency, preferably, if we can constrain the inconsistency in our system to only being in the internal data, but the outputs remain consistent. That would be optimal. And in a lot of situations, we can do this. But some inconsistency has to leak out to the outside world. We know this from the CAP theorem. So since something has to leak out to the outside world, something has to be inconsistent, something has to be, in some sense, suboptimal. Our goal is to find out what those outputs can be. What are the permissible inconsistencies that we can get away with? So some of the inconsistency has to leak into our outputs from the CAP theorem. For example, when a node crashes or disconnects, it cannot receive updated data. And if it cannot receive updated data, it won't have the latest version of that data. And if it doesn't have the latest version, they're not in sync. And if they're not in sync, they're going to do different things. And if they do different things, it is inconsistent. And the question is that okay? Are there some inconsistencies that we can get away with? So that will be the topic for the next chapter. Will be about consistency. How do we deal with consistency and what even is it? Let's first figure out what it is. So, after the break. Let us then continue. All right, so where were we? We wanted partition tolerance and we want availability. And ideally, we do also want consistency, but we know that we have to give it up at some point. So the question then is, what exactly is inconsistency? And then, naturally, is there something that we can do in our codes that makes it so that inconsistency is impossible? Because if there's something that we can do to make inconsistency impossible, then we're only left with consistency. So that would be nice. So first, let's think about what exactly is consistency. What does it mean? In distributed systems, when we talk about consistency, we mean that the replicas agree. We mean that the different nodes in the system have the same data, and when asked for what that data is, they respond as an output with the same data. So an output, just to make that clear, an output is just the data that you haven't written to the outside world yet. Right? So in order to know what to do to the outside world, in order to perform an output, you need to know what that output is, and what that output is just data. So an output is just data, and an input is also just data. Right? Just to make that clear. So in distributed systems, the replicas agree on what the data is, and they agree on what the output should be. In formal logic, we mean that it is free from contradiction. Now, do notice that these are the same thing. Right? In a distributed system, a contradiction would mean that one node produces an output that is different from what another node produces. That would be a contradiction. And also in formal logic, if you have two different actors or two different participants of any kind and they don't agree on what the thing is, then you have inconsistency. So the question is, how do we end up with inconsistency? Or what are the prerequisites to create inconsistency? Or formulated yet another way, what do we send or not send between nodes in order to create inconsistency? Because if nobody sends anything, then everybody agrees on that there is nothing. And now we all agree. And the moment you start communicating, then messages can get lost, duplicated, reordered. And that's the first time where you can actually introduce inconsistency. If everybody starts with nothing and continue with nothing, there's no inconsistency. So what are these prerequisites? There are two of them, two prerequisites for contradiction. You need self-reference. In our code, that would be something like recursion or looping. And you also need negation. In our code, that would be things like not, delete, reverse, reset, and so on. Since our code needs to run forever, it will have loops. Which means that the only thing that we can play with now is the negation part. Let's look at some examples of why this is a contradiction, why these two things are required for contradictions. Think of them as paradoxes, right? This sentence is false. This is a paradox because it has self-reference and negation. If we remove the self-reference and say that sentence is false, there's no paradox. Or if we remove the negation and say this sentence is true, then it's no longer a paradox. The set of all the sets that do not contain themselves. Classic paradox. You see the negation, you see the self-reference. Another classic paradox. It is opposite day today. You cannot create a paradox without self-reference and negation. I would say that's like homework for next time, but no, I don't want you to. Well, if you do, here's the homework for next time. If you find a paradox that does not contain self-reference and negation, I would be very curious as to what it is. Because as far as I can tell, that is impossible to do. You cannot make something contradictory if it doesn't contain self-reference and negation. In fact, the word contradiction literally means against itself. The word contains the two precursors for itself, right? It contains the itself, the addiction part, and the contra, the against, the negation part. So it's a very explanatory word. So our code needs to run forever, so it will have loops, and the only thing we can work with then is the negation. So we have really reduced distributed systems down to one thing now, really. It started with, we can do whatever we want with the network. Messages can be gained, messages can be lost, reordered, duplicated. We need to resend in some kind. We have the cap theorem. We need partition tolerance and availability. The only thing we can work with is consistency. In order to work with consistency, the only thing that we can really work with is negation. We have reduced all of distributed systems down to a couple of concepts. Minimize negation, or get rid of it entirely, and make it so that our system is idempotent and commutative. If we have these things, now we're really cooking. But we have really reduced distributed systems, the entire fields, down to just a tiny amount of things. So let's see what we get. So far, on the negation side, we have to sacrifice consistency. We don't want inconsistency to take over our program and its outputs, because if it does, it means that it does the wrong thing. The inconsistency has to come from self-reference and negation. We need the loops, so the only thing that we can control is the negation part. So the conclusion is we need to be very careful and very precise with the places in our code where we have negation. Deleting things, undoing things, not operators, going backwards, reverses, and so on, that is the hard part. And we need to get rid of those as much as possible. If we are not able to get rid of our backs and our deletes and so on, then we will produce a system that has inconsistent outputs, and therefore it will have incorrect functionality. You with me so far? Another so far slide. On the filtering side, the messages can arrive in any order. If we accept the disorder in our messages, the data and the outputs will be utterly inconsistent. That's the other branch. Right? That's the first branch that we walked through. So we need to impose some kind of ordering on our inputs. And we need to impose that ordering based on the data about what we have received previously. So the only place to impose this order is when we are receiving. We can't impose that ordering when we are sending because the network can mess with our messages. So we have to do it when we are receiving. And when we are receiving, we can't choose what to receive, but we can choose what to ignore. So the only way to do this is by discarding messages. And the question is, why does that work? Why can we impose ordering in the messages we receive by only discarding messages? Well, the reason why it works is because it limits the possible negations. Now we need some examples, because without examples, this is going to become way too abstract. So let's do some examples. And I have quite a few of them. Let us start first with the most basic example of them all. A binary value. Let's tie this directly to the elevator project as well. All right, so we have an order of some kind, a button press. There exists an order, a call, a request. It is represented as a 0 or a 1. Either there is no request there or there is a request there. Our goal is to make a system that, when the button is pressed, it informs the other nodes about the new order. So we are making some kind of order distribution thing here. And we only have a binary value to work with. This system will have some inputs and some outputs. It will have 3 inputs. The first one is obvious. The button is pressed, so that's the button press. Somebody presses the button and something happens. The second input is maybe a bit less intuitive, but we do need it as well. At some point, somebody has finished executing that order, and we need to clear it so that it doesn't exist forever. And on the output side, we have the order value, right? Either there is an order or there is not an order. And then as part of our intermediates, we have something happening on the network between the different nodes. Are you with me in the example so far? The constraints of our example? So we need some kind of algorithm. Well, if you can even call it that. So what is our algorithm? Well, the algorithm here is super naive. Let's start with something super naive and, well, let's see what happens. If somebody presses the button, we set our local state to 1. If we have finished executing the order, we set our local state to 0. Right, makes sense? And then if we need to communicate it on the network. So if we have a 1, we send a 1 to the network. If we have a 0, we send a 0 to the network. And on the network side, somebody else could push the button and somebody else could finish the order. So if we receive a 1 from the network, we set our own state to 1 because somebody else says that there is an order. And if we receive a 0 from the network, that means that somebody else has finished the order, so we also say that the order is finished. So if we receive a 1, we set our local state to 1. And if we receive a 0, we set our output to 0. Do you see what the problem is? Think, we are periodically sending here. they all start with a 0. Somebody pushes the button at node A. It is communicated on the network. So A sends a message on the network. It arrives over at C. Right? Make sense? Oh yeah, by the way, there's also still sending. So B has a 0, and it is sending a 0. So since B is sending a 0, it's going to arrive over at A. What's happening? It really is just a case of first come, first serve. Whatever message arrives will overwrite the other one. It is a classic race condition. Classic distributed race condition. So we'd have no ordering here. It is impossible to make any changes propagate because chances are it will just be overwritten by the rest of the network. It's a race condition. Like the latest info will overwrite. We don't discard anything, right? So let's think instead, if we get a 1 here from the button press, somebody pushes the button, we get a 1. And it propagates over here, back to like the first scenario. This 0 that B is sending, it's trying to delete an order that we are trying to distribute. How do we make this message that's coming from B some kind of invalid? Right? So the only way to propagate this 1 is to discard the 0. So let's try that. Let's try a different algorithm. If we have a 1, or if we get a 1, it will overwrite the 0. If we have a 1 and we receive a 0, we will discard it. So B sends a 0. We receive a 0 here on A, but we already have a 1, so we discard the 0. We receive a 0 here, but we have a 1, so we discard it. And eventually this 1 that we were sending from A and the 1 that we're sending from C will show up over in B, and it will overwrite itself with a 1. Now do you see the problem? How do we set a 0? Okay, A got the button press and A also executed the order, so A tries to set its value to 0. So it sends the 0 to C and it sends the 0 to B and saying, okay, we're done, we've finished the order. Order is completed. Well, the 0 is ignored because we have a 1 here, and the 0 is ignored because we have a 1 here, and then the C sends the 1 and the B sends the 1, and it is automatically just reset back to 1. So it is impossible in this scenario to delete orders. So how do we deal with this? A binary counter, either we get a race condition or we get a situation where it's impossible to go back. You see this? If we have a system where the requirements are distribute the number 1 to everybody who has a 0, and then once everybody has it, the system is correct. That wouldn't be a problem because there is no negation. But the moment we have the negation, we need to go back to 0. That's when the problem occurs. So instead, we need some way to go forward instead of going back. So what happens if we, for example, add an intermediate step, like an unconfirmed order? Well, that's on the correct track. Now we're getting somewhere. Exactly how it's going to work? We're going to get back to it. Let's do some other examples in the meantime. Here is the core problem. The system has negation. It has both an add an order, and it has remove an order. If we didn't have this remove order operation, the system would work fine for some definition of fine. If it was correct to only distribute orders and only add stuff, it would work. If the moment we also need to remove stuff, it stops working. Let's do a different example. Just a collection of stuff. We have a distributed collection of stuff. It doesn't matter what the stuff is. It's just some stuff. So let's just do some letters or something. We need operations to add and remove. You can probably already tell that the remove part is going to be kind of hard, right? So what is the algorithm? Let's start with the basic algorithm, a discard nothing algorithm. So the output is just the union of whatever we have locally and whatever we received on the inputs. So the union is just both, right? So let's just do numbers again. One of my favorite numbers, the number 5. C has nothing. It receives a 5. What is the union of nothing and 5? It's the number 5. B has a 7, because 7 is a nice number. It sends that to A. What is the union of 7 and 5? 5 and 7. A sends its 5 and 7 to C. What is the union of 5, 7, and 5? 5 and 7. You see how this one will eventually start, like adding a number, it will start propagating out into the network. If we add another one here, do we have any other cool numbers? Any favorites? 0? 0 is a nice number. If we add a 0 here, it's going to start sending 5, 7, and 0. It's going to start distributing and so on. Now the question is, we wanted to delete the 7. C is like, you know what? Delete the 7. Just 5 and 0. How do we delete this number from the collection on the other nodes? All right. Our algorithm is union. What is the union of 5, 0 and 5, 7, and 0? It's 5, 7, and 0. So this one's going to keep the 7 because that's the most amount of data. So this algorithm does not work. We cannot delete in this way. The union will immediately re-add the lost data back to us, right? So this one sends a 5, 7, 0. We have a 5 and a 0, and it goes, oh, we're missing the 7. So it immediately gets put back on, even though we just had a 7 here that we deleted. It will immediately get re-added. So this algorithm doesn't work. Why does it not work? The problem, negation. The solution that we need to impose, we need to discard. We need to discard the message that says that the 7 should come back. How do we discard this message? So what is the solution? Do you see any? The solution is to not remove. You can't remove. It's impossible. The moment you remove something, the network is going to re-add it. So you don't remove. We need to have some other solution to this instead. We have two options here. One is to send a special message that says, delete the number 7 specifically. So let's try that instead. We're back at the 7 here. And C is trying to delete the number 7. So it sends a unique special message, which isn't just, this is what my content is, by the way, take the content. It sends a specific message over the network, which says, delete the number 7. Or is it better to have like a 7 with a tilde on top of it or something? It doesn't matter what the notation is. I don't really care. Delete the number 7. And A goes, oh, I got a special message. Delete the number 7. I will delete the number 7. Great. We have packet loss. This message never arrived over at B. And B never got the message to delete the number 7. And it will immediately re-add the number 7 back. So it's on the right track, but it doesn't work. Not entirely. Do we have any other options? Well, what happens if we add the not 7, instead of removing 7 and sending a special message? We keep the 7, and then we add our special not 7 afterwards. Okay, this one also keeps the 7 because, well, it's going to keep everything. And it sends the not 7 message on the network. And eventually this one will also propagate over here. We're not removing anything. We are just specifying that it should no longer be considered. It isn't gone, it is just marked as unavailable. This is how most content delivery networks work. If you upload an image to your favorite social media site and you're like, you know what, I'm going to delete it. You're not deleting it. You're just sending a message that says this content should no longer be available. Because removing content is actually super hard. It is so hard that it is actually easier and cheaper to just send a message with a token that says it should not be available and just keep it in storage. Buy more storage is a cheaper solution than trying to actually fix the problem.
Don't we have a problem when we want to add 7 back? Like after removing it?
Yeah, you do have a problem when you want to add the 7 back. So what you need to do is add, okay, this was the first time we saw 7, and this was delete 7.1, and then we have a 7, which is the second time we add a 7, and so on. So yeah, you have a problem. And that's not the only problem. You also have another problem, which is that, well, it's going to grow forever, and we are making embedded systems, and they don't necessarily have infinite memory. So we really do want to remove stuff. We want to see if there is some way to actually properly discard all the things that are deleted. Is there some way to know that everybody on the network knows about this operation to get the 7 and delete the 7, and so that everybody on the network knows that, okay, we actually mean it? And that's where your counter comes in, right? Because if you delete the 7 and you go, oh, I have 7.1 and I have 7 not 7.1, that means I can delete them from memory. Because 7.1 and 7.2 are different 7s. So that's where your counter comes in. But now we have a different problem, right? Guess what the next example is? The next example is your counter. All right? What happens if we have a counter that only counts up but cannot skip numbers? A monotonic counter. Here's the algorithm. I'm sure you are familiar with the plus operation. If the message is not +1 from us, we discard it. Do you see the problem? Do you see why this is impossible? Or do I need to explain it with the chalk? All right, if we fail to receive the message, this one goes 1, and this one goes, yep, I acknowledge your 1. And this one goes, yep, I also got the 1. And this one goes 2, by the way, actually 3. And this one goes, well, 3 is too much over 1. It is not +1, it is +2. I reject. And it will stay at 1 forever, because the rest of the system has moved on. So this is too strict. This requires waiting for everyone, so it is not partition tolerant. We don't tolerate arbitrary message loss. This is requiring too much consistency from the system. So we can go too far the other way. We are discarding too much. So let's try discarding slightly less. Let's try a non-monotonic counter instead. So a counter that only counts up. So we only have the upward direction, we have no negation, but it can skip numbers, so it's not monotonic. So think of it as the latest version. So node C here, it goes, or A goes 1, I'm a version 1, version 2, version 3. C goes, yeah, I received your version 1, never received your version 2, but 3 is greater than 1, so I accept your 3. And then B is like, I have version 1 for you, number C. I have a version 1 for you. And it goes, well, I already have version 3, so I don't care about your version 1. So the one that is sent over here, it gets rejected because it's less than 3. But the 3 that gets sent in the opposite direction, it gets accepted because it is greater than 1. You see this? So a non-monotonic counter is probably the simplest functioning distributed system algorithm. There's no negation because we're always counting up. It is commutative because it doesn't matter if we receive version 1 first or version 3 first. If we receive version 3 first, we stay at version 3 forever. If we receive version 1 first, we first get version 1, and then we get version 3. So it is commutative. And it is also idempotent. If we receive the 3 and we receive the 3 again, well, no matter how many times we receive the same version 3, it doesn't matter, we're going to stay at version 3. So no negation, commutative, idempotent. This is the simplest system that actually does something useful that works. The problem is that, well, we can only go up. And if we want to go back down again, well, rip. Or is it? All right. So what was the algorithm? Any number less than ours is discarded. So that's the way we achieve it. We achieve it by discarding. So as long as we never need to go back, this will always be eventually consistent. Eventually, they will all end up with the same data. In an intermediate time frame, they don't have the same data, but eventually they will all get the same data. So the old data is overwritten by the newest, and it propagates through the network that way. Missing a number, if we miss version 2, it doesn't matter. It is defined as part of the specification to being able to skip numbers. This is defined as not an error. Now the question is, can we take our monotonic or non-monotonic counter and can we add a reset to this? Are we able to make it so that once we have reached some number n, we are able to go back to 0 or back to 1? Is this possible? Are we able to add some negation to this in such a precise and surgical way that we don't get the big problems of negation in general? And well, would I be talking about this if it wasn't possible? Of course it's possible. So the goal is to make a counter that counts up to n, and when it reaches n, we can reset it back down to 0. What would the algorithm have to be? Remember, the algorithm is based on discarding messages. What messages do we discard in order for this operation to be possible? Well, the first thing is we're making an upward counter. So the first thing to do is do not count back down again. So if we have any number that is less than or equal to ours, we discard it. That lets us count up from 0 to n. But we need an exception, right? If the value is n, we can go back down to 0. So we do not discard the 0 if we are at n. This lets us reset. Or it lets someone else reset it for us. Is there anything missing? You see the missing link? Remember, what happens if n is 1? Now we have the binary counter. So there's something missing here. And the missing thing is, well, we cannot just immediately go all the way back up to n again if we are at 0. Because otherwise, well, we just reset back down to 0, somebody else still sending the n, we receive the n, and we go whoop, right back up to n. So we need some way to not reset the counter when it is being reset. So I invented a new word called unreset. So do not unreset. That's a triple negative for you guys.
What should we do if we are in a number between 0 and n?
If the number is less than yours, you discard it. If it is greater than or equal to yours, or if it is greater than, you accept it. So let's do an example on the blackboard, right? They all start at 0. What is our value for n, by the way? Does anyone have a preference?
68.
It's a bit high, isn't it? I mean, it's nice, but it is a bit high. I'm thinking more like 4 is also a pretty decent number, because we don't need to count that high. Okay. A initiates. We start at 0. Everybody starts at 0. Everybody is happy. A initiates, and it counts upward. Where? Oh, there we go. And it starts counting upwards, and it goes to 1. I'm just putting them next to each other so you can see the progression. This is an override operation. That's not storing both of them, just to make that clear. What happens if C sends to A? 0 is less than 1, discarded. Same thing from B. 0, less than 1, discarded. A sends to C. 1, greater than 0, acceptable. Overwrites with a 1. So the 1 will propagate. Let's say A now, for example, increments onto 2. 1, less than 2, if we send that 1, discard it. 1, greater than 0, if we send that 1, it would be accepted. But let's say instead we have some communication errors between C and B, so 2, greater than 0, yes, accepted. And it is none of these special cases where 0 or n, acceptable. Let's say B continues with a 3. Greater than? Yes. Greater than? Yes. We see how we can increment as a monotonic counter. Actually, fuck it, let's set n to 3 because then I don't need to write anymore. What happens now? No, screw it. Let's do 4. A and C are primed and ready to transition back down to 0. So A and C can transition back down to 0. Do we see a problem here? There is one missing link. One more missing thing. B never got to 4. So what happens if this one transitions to 0? 3 is greater than 0, boom, 3. So we're missing one thing. What is the thing that we're missing? We need some kind of barrier. We need to wait for everybody to have the value of n. And not everybody on the network has the value of n here. But once this 4 has propagated over to B. Once everybody is stopped at that barrier and waiting on the value n, now we can transition. What happens if C triggers a reset back down to 0? It sends a 0. This one has the value of n. The number is less than ours, but there's an exception. We do not discard the 0 if we are at n. And we are at n, so we discard. Or so we do not discard, we accept it. Now if this one was not at 0, and it receives a 0, it will go, well, that's not acceptable. So it wouldn't do anything, but we needed the barrier anyway, so.
That's how the overall network will know that every node gets to the number.
Yes, exactly. How do you know that every node on the network is at the barrier value? So it has some problems. Compared to a non-monotonic counter, the moment we add the reset, the moment we add the negation, you see how we get problems. We just wanted a simple reset. We had a pretty decent algorithm for getting that reset, but we still have some problems. So we had the pulling forward problem. After triggering that reset, if we triggered the reset like this one sends a 3, 3 is greater than 0, it goes boom, 3 immediately. It immediately gets pulled forward. That was the first problem. So we solved that problem by introducing a barrier and saying, okay, you are only allowed to trigger a reset if everybody on the network is at the value of n. My question is, okay, how do we know that everybody on the network has a value of n? It also has some availability problems. If we are waiting for a barrier, well, we're waiting. If we're waiting, we are not available. If we're not available, then we might have a problem. So what's the solution here? We need to not wait for everybody on the network. We just need to wait for the ones on the network that are alive. Does that make sense? So we only wait for the alive nodes. And we also have another problem with the initial value. What happens if a new node joins with, I don't know, a value of 2 now? So D joins and it starts with a value of 2. Like, what is the correct approach to dealing with this? Should these two jump forward? Should these two be pulled forward? Should that one be pulled back to 0? Or is it forward to 0? What, if we have a cycle, what is backwards and what is forwards? So this one also needs a solution. Well, the solution is don't start with a known value. Start all of your interactions with a question mark value of an unknown. And then don't send anything before you've received the first message. Or send your unknown value and everybody discards the unknown value. And the final problem, which is we're not going to even deal with because it's too hard to solve, is partitioning. What happens if you have multiple connected groups that all think they have the correct value? How do we deal with this? So there is something missing. This isn't perfect. But it is pretty close. Instead of sending just the numbers, instead of sending just what position are we on in the counter, we also need to send who we are. In order to trigger a transition, everybody needs to wait for that 4 from everybody, right? I think this might answer your question before you ask it, but so give me a second, but I see you. This one triggers a reset, or this one triggers the value of n, the 4th value, the end of the cycle, before we reset. This 4 isn't just, we're not just sending the 4, we are sending 4a. So this one contains the information 4a, and this one receives the 4. And of course, it doesn't just receive the 4, it receives the a as well. But since we are C, we also receive the C, because we are C. This message gets sent over to B. It gets the A and the C from C, and of course it is B itself, so it gets A, B, and C. And this message, let's say this message shows up to A as well. It gets the A, B, C, and A, which, what is the union of A, B, C, and A? What is the latest version? Well, it is A, B, and C. We're just adding to a list. This is the list adding problem. We are just adding, we are not removing. We are joining forces with example 3, 2, 3, I don't remember. Right? This is a list adding problem. And the list adding will propagate, and eventually we go, oh yeah, these are all the ones that are alive on the network. Now the question is, where do we get this alive list from? And how do we maintain the alive list? But assuming we have a list of who is alive on the network, we can fill in this one. We know that this is the nth step. What is the transition to go back down to 0? What is the trigger for this event? The trigger is that we have heard the n step from everybody on the network who is alive. So C knows that A, B, and C are alive on the network, and it knows that it has heard step n from A, B, and C. Therefore, it can automatically transition over to the reset state. If it hadn't arrived over here yet, we had only heard from A, it would go, well, we haven't heard from A, B, and C yet, so we cannot transition over. But the moment it shows up, it will transition over. The moment it receives this message, it will transition over. Now your question.
Is there a possibility that a disconnected node would come back at time?
Yes. Is there a possibility that a disconnected node comes back at an unfortunate time? Yes. And what is a disconnected node that comes back? A disconnected node that comes back is a node that comes back with an initial value. So the moment you notice yourself get disconnected, you have to say, I don't know what the state of the network is. I have to go to the unknown state. Because I am disconnected, I am alone, so I need to be able to assume the state of the rest of the network so I don't interfere with them when I come back. That's the only solution to that problem. Is this good enough of a solution? We're combining the non-monotonic counter with the list appending operation. We're doing a non-monotonic counter up to n, and then we're doing the list adding operation there, and then we do an automatic transition over to the reset state. We are really combining solutions here, but is that enough? Now maybe you see why distributed systems are so fucking hard.
And what happens if, for example, a network divides into two parts?
Yeah, what happens when a network divides into two parts? Well, I put it under problems on partitioning, and I put it in gray because it's so hard that we're not going to talk about it. And there is also a reason, and this is one of them, why network partitioning is on the project. It is assumed that you should not even think about what happens when you have multiple groups of multiple elevators in a system. First of all, it requires that you have at least 4 of them, which you won't have. And second of all, the problem is so hard to solve that it's not even really worth it.
As soon as either A, B, or C receives that the others have come to the end place,
Mm-hmm.
want it to reset back to 0 and not send that itself has come to the end place to the other nodes?
I need to remember what the question is well enough to be able to say yes to it, but I think the answer is yes. So can you repeat the question so I can say yes?
If, let's say A and C has, A and C, and then C sends to B, A and
And B, of course, will add itself, yeah.
Won't it then reset back to 0 before it can acknowledge to A and C that it has come to the end?
Yep, correct. The answer was yes. So I was correct. The answer was yes. Good. So the question is, okay, this one receives information about this. B receives information that A, C, and B, which is everyone, have reached the nth step and will immediately transition itself over back to the reset state. These two nodes do not know about A, B, and C. They only know about A and C, respectively. They don't know about B, so they will not transition over to the reset state. Because the moment this one has reset over, it will lose this information about A, B, and C. It will just have the 0, and it won't have one, and it will have an empty list again. So how was this problem solved? It was solved by the algorithm. What happens? B sends a 0, and we are at n, and this one is at n. And if we receive a 0 when we are at the nth step, we go, oh yeah, somebody else on the network knows that everybody knows. So C, as a part of observing that there comes a 0 from someone, it knows that that someone where that 0 comes from knows that everybody on the network knows that it is okay to reset the loop. So it will not reset itself, but it will reset as a function of B knowing about it. So that reset will not happen, but the reset from the other node knows. So we do, yes, we need trust in the system, right?
What if B can get an update and get to 1 before it can send the 0 to A and C?
Okay, so the question is, what happens if B continues up to the 1 state before it can send that 0 on? Now we need to ask ourselves, what is the cause of that 1? Right, so something over on node B, something on the external world as seen from B triggers a continuation back upwards to 1. Yeah, well then you're kind of screwed.
Why don't we make a central node that make all this synchronization between all the nodes?
Well, yeah, why don't we just make one central node? Yeah, well, why don't we?
If the central node goes out, everything.
Yeah, well, yeah, if the central node goes down, then if it had critical information that wasn't distributed, we're screwed. So we need to distribute that information. The question is, how do we distribute that information? Well, we need to distribute it in such a way that it is consistent with the other nodes. And now we're just back to square one, possibly. But maybe not. Sometimes it is okay to have a central repository of a single source of truth. And if it isn't updated properly, then it isn't updated properly, and that's a permissible inconsistency. Now, if that inconsistency is permissible, well, now we're okay. But if it's not permissible, then we're screwed. So yeah, back to the what happens if B starts transitioning over to 1? Well, you could add a double barrier. That's the solution. Most of the time you don't need it, but you could add a double barrier. Say that, okay, we're doing a barrier here, and we're doing a second barrier at the reset step. And then with a double barrier, you can make sure that everybody not just resets, but everybody has reset before you continue. So it's a solvable problem, but we get into like the engineering of it, which is it worth solving? So yeah, the cyclic counter, this might be the precision targeted reset that we want, but it has its problems. You need to combine the non-monotonic counter and the list adding problem, and a barrier, and possibly even a double barrier for it to work. So it is not the easiest thing in the world. But it does solve a lot of problems. So messages can arrive at any order. how we react to the counter value message depends on our counter value. We either update our value to the received value if it is acceptable, or we do nothing if it is not acceptable. And we can go back to the start after we reach the barrier. Now think, what happens if we draw this out with circles for our counter values and arrows for the received counter messages? And I'm not going to do this on the blackboard because screw it. Because, frankly, this may, for many of you at least, be what you will be doing as preparation for next week. Think about it, because this is a state machine. Our order states are something like, we don't know if there's an order. There is no order, so we know that there is no order. There is a new order that is possibly unconfirmed or something, or we have a confirmed order or something like that. Okay, how many of these states do we need? How high is n in our abstract counter? We want to make state transitions, so we have a cycle of states, and we only go upwards in that cycle, so we don't transition backwards in our circle of states. Ask, what are the conditions to move to the next state? What state has the barrier? Because we need to have a barrier someplace that says we need to wait for everybody to know about it before we can continue. Now, I would suggest something like, you don't continue unless everybody knows that there is an order there, because that's when you can set the light on. So something with a light matters here. Exactly what? I'm not going to tell you that. You need to figure something out on your own. And then we only perform the outputs on the consistent data. So we have internal inconsistency. This internal state, it can be whatever it wants to be. We don't really care. But the outputs, well, on the elevator, either there is an order there or there is not an order there. There aren't any intermediates. We don't need to tell the light, you can turn on-ish. Either the light is on or it is not on. Either we are executing that order or there is no order to execute. We're not like, execute-ish light, maybe? That's not a state. So the outputs should reduce our unknown, none new, unconfirmed, confirmed, whatever. And I should reduce that into yes, there is an order, or no, there is not an order. Does that make sense? There are some more pieces of data that have non-counter-like structure to them. I'll just cover these and then we take a break, I guess. There are some non-counter-like data. The peer list, for example, who is alive on the network? We needed that for this thing. So we need to, oh, did I write peers as like a PAR? Okay, that should be PER on line 2. We need to add and remove peers with a PER. I am spelling good, yes, very. So if we need to add, that's okay. We need to remove, we have a negation problem. Do we have a negation problem? No, because we're not actually removing anything. We're not communicating with the rest of the network that we are removing something. We are removing it on our own. And since we're not communicating removal with the network, we don't have a negation problem. And then we have the elevator data, like where is the elevator, what is it doing, is the door open, at a floor, what direction is it moving, that kind of stuff. For that, we only need the latest version. And we have a single source of truth. So since we only need this, the latest version and we have a single source of truth, which is the elevator who is communicating its own states, we don't have any negation problems there either. And without any negation problems, it's eventually consistent. So there are some data like these two which are much easier to distribute. Because, why? Because they don't have the negation problems. And they are idempotent and commutative as well. So, a break time, I think. And after that is going to be the conclusion part, and then I'm going to do some extras on topology, network topology, as well as one more thing which I don't even remember what it was. So that could be interesting when I don't even remember what my slides contain. But yeah, let's just do, let's keep it like 10 minutes. So back here at 3:25. Yeah. Okay, conclusion time and then extras time afterwards. So far, we need some way to control the negation in our system. Because the problem with distributing data is, well, it's negation primarily. So the only way to deal with inconsistency is to be careful and very precise with the use of negation in our code. So resets are hard, deleting is hard, nots are hard, and so on. The only place where we can do that is when we are receiving messages. So the only way to solve this problem is to discard messages that are in some sense unacceptable, for some definition of unacceptable. And the way we do this is that we formulate our data as states, we formulate our messages as events, and we create a state machine. Because the state machine is the most structured way to deal with, well, not transitioning on to the next state. So a state machine where every message you receive, you transition to the state that corresponds to the content of that message, that would be just override everything. But we want to discard stuff. So the only way to structure discarding in a sensible way is to make a state machine out of it. I'm not going to do that in exacting detail today because I want you to try it when you are preparing for next week. The alternative is if you have some opportunities to avoid the need for negation. So if you don't need to remove stuff, you can only add stuff. Then you don't have this problem. And as we have learned, the best way to solve a problem is to not have the problem in the first place. So if you have any kind of latest version-like data, then you don't have this problem. If you have any kind of single source of truth data, then you also don't have this problem typically. Especially if you combine them, you definitely don't have this problem. And also if you have any kind of lack of message is information data, like the peer list, you stop receiving from the peer on the other side, then that means there is information there. In that case, since you're not sending anything to them, you're just not receiving from them, you don't have this negation problem. And on the other side as well, there are some places, well, you need availability, you need partition tolerance, so inconsistency is something that you're going to have to deal with. There will always be some amount of inconsistency, assuming you still want availability. The question is, find out from the specification, find out what is the permissible inconsistency. What kind of inconsistency in our outputs can we get away with? The thing is that what is permissible depends on what the system does. So what constitutes a correct output but inconsistent output? Correct but inconsistent output. What is that? Depends on what the system does. It depends on the specification for the system. This means, and this is probably one of the most important things from today, which is that there is no general purpose solution to distributed systems problems. Because you need to find out, can I live with partition tolerance or no? Do I need partition tolerance or no? Do I need availability or no? If I need inconsistency, what inconsistency is permissible and what inconsistency is not permissible? All of that is entirely application dependent, which means that there is no such way that you can just import a distributed systems module and use that. It has to be application dependent. And this is why distributed systems are so hard. So let's just take it all the way from the top and recap and see if we refresh our memories and see if we can follow the logical chain all the way. The process output depends on the inputs. we only care about the inputs and outputs to the outside world. All of the things that happen in the intermediates, we don't really care about. So these intermediates, the network communications we do internally between our programs on different nodes, and the data representation that we have internally in a single program, we don't really care what that is. There must be some amount of inconsistency to achieve availability and partition tolerance. The question for us is to figure out what that inconsistency has to be. And we want to focus most of that inconsistency to the intermediates. So our intermediate representation when we're communicating is, well, it's going to be kind of weird and everybody's going to be uncertain about what the other ones know. But as an output, you should be able to, most of the time, get consistent outputs. But some inconsistency has to leak out into the outside world. If you disconnect a node entirely and you have to keep going, there will be some amount of inconsistency. It's simply unavoidable. So the question is, can you find that permissible inconsistency and live within those constraints? When you are trying to control inconsistency, the only way to do it is with the careful application of negation. Try to avoid resets, try to avoid deletes wherever possible. You can't get rid of the self-reference, so the only way to solve it is with the negation. The only place you can do that is when receiving data. You can't do it when sending because the things that you send are going to be lost and reordered. And the only way to do it is to filter out messages. You can't change the content of what you receive. You can just discard the things that you don't like. The messages that you filter out are going to be those that violate either one of commutativity or idempotency. So for the latest version, you throw out the ones that are from a previous version because they violate commutativity and idempotency, for example. Or when you're adding to a list, you throw out the ones that contain less than what you have because they contain less, so they're not important, so you throw that out. Now, when you do need some kind of negation, you want precision negation. And usually it's going to be some kind of barrier that waits for all of the alive nodes on the network. There are not a lot of other ways to do negation. You either need to avoid it or you need to do some kind of precision work. And the precision work that is most applicable is the barrier. Oh yeah, here's what the slide is for the extras. First extra, explicit resending. So for now we've focused on everybody is just periodically sending. And I haven't really said anything about explicit resending, like when you fail to get an acknowledgement, what do you do? And the reason why I haven't said that much about it is because it's kind of boring. So we've focused on periodic sending. So the message is just a copy of the local data from the other node. That's what it's sending. It's just sending, this is what I believe my view of the world is, and I am just sending it to you, and it's up to you to figure out what to do about it. So the receiving node takes its worldview, its local data, and then the worldview of the remote node and combines them to figure out what is the state transition going to be. Like, what is the event? The event is the difference between what the other one says and what I say. So that we're calculating the event based on the difference between the two worldviews. Now you could send the event directly as a delta and say this is the transition and just send the event yourself, but the problem is then the sender needs to calculate what that difference is. I don't even understand what I've written here. Oh yeah, so if you are sending in the periodic sending method, you know about an order. Node A knows about an order, node B does not. So it's just sending data that I know about an order that you don't know about yet. So if you're transitioning this into an event kind of explicit message, then you would send a new order message. On the barrier side, we're waiting for acknowledgements from everybody that's alive. So you're filling the list of everybody who's alive. Instead of just filling that list and periodically sending, you send a specific message, which is a confirmed order message. And you can send that over the network. So this might be more intuitive for some of you. to think about it as explicit messages, like when this happens, send this message one time. And then if we don't get a response, send this message one time. Or if we don't get a response, don't do anything and let the user press the button again. It might be more intuitive to work this way rather than to work with periodically sending worldviews. But ultimately, they are the same thing. The only difference is the regard to resending. If you are explicitly sending a new order message and it doesn't arrive, you need to perform the resending yourself. So you need to pay attention to any acknowledgements or lack of acknowledgements yourself. But if you're periodically sending your worldview, then the resending is just a part of the standard functionality. So the only difference is the regard to resending. So that's why I haven't really considered it, because I consider resending to be a solved problem. Just send periodically, and that's your resending. The second extra is on topology. I have gotten some questions about like, what even are these things like master-slave and peer-to-peer and circle and mesh and so on. And I've also gotten some, a slightly better question perhaps is, which one should I use? And it's also a slightly worse question because these are trade-offs. They're not like, oh, everybody should do this, because they're not, well, they're different, which means that they are good at different things. So the first one is the master-slave architecture. So what this is, that you have n slaves that are connected to a single master. And there are no connection between the slaves. So I'll just draw it out on the blackboard because why not? So you have the master node. Fuck it, let's just do 3. Let's keep it as. And then you have the slave nodes. Right? You're familiar with this kind of structure, so there's no connection. Can I do that? No, I cannot. There's no connection between the slaves. There's nothing in between them. There is just the direct connection to the master. So if one slave needs to talk to another slave, they need to go via the master. So strengths and weaknesses. One advantage is that since you have a master, you have a single source of truth. So if the master calls the table of what are the orders in the system, the slaves don't really get to debates about that one. It's whatever the master says goes. And since you have a single source of truth, you can just periodically send it, and all of your consistency problems might actually just straight up be solved right there until the master dies. So since you have the single source of truth, you can do the latest version like periodic sending there. A disadvantage is that you need to be able to migrate the master when it dies. So what happens when the master dies? Everybody's connected to nothing. So you need to reestablish and promote one of the slaves to the new master. That's one problem. And then you have a different problem. You promoted this one to master, and now everybody is connected to this one, and everything's fine, and then the original master comes back and is like, I am the master, and it tries to connect everybody back to it, and you have a conflict here, like, who is the master anyway when you do this? Or maybe it comes back as a slave instead of comes back as a master. Maybe that would solve it. Well, you need to figure that one out. It's a disadvantage. You need to figure out the arbitration between who is who and what does what. Make sense? Good. The next one I want to talk about is a circle. That's a very nice A, isn't it? There we go. So in a circle, given the name, everything is connected as part of a circle. So a single node has a previous node and it has a next node. And no matter how many nodes you have in the system, you only have one previous and one next. Make sense? So you know that if a message that you are sending on the circle manages your message. if your message manages to traverse all the way around the node, the circle, you know that it has been via all of them. So if you send a message on the circle and it arrives back to you, it means everybody has received it. So that's a kind of acute advantage. Another advantage is that at least for embedded systems where you really want to avoid dynamic allocation, the data structure for this is very simple. You just have a next and a previous. It's just straight up a linked list of pointers to connections. So that is useful in some applications, especially for C programmers. So it's an advantage. It's not necessarily a very big advantage, but it is one. But it also has some disadvantages, which is the more packet loss you have, if you have a 20% chance of losing the message here and another 20% there and another 20% there and another 20% there, the accumulated chance of losing a message that is going through the entire circle starts becoming quite high. Because now you're taking 0.8 times 0.8 times 0.8 times 0.8 chance of it going all the way through the circle. So more nodes, higher chance of failure. And also then, if the more nodes you have, if you have 10 nodes, the chance that it goes through all 10 of them without losing a packet becomes lower. And if you have 100 nodes, then the probability is basically zero that it's going to come through. So the more nodes, the less reliable it becomes. And for a distributed system, the point of having more nodes was to make it more reliable, not to make it less reliable. So it has that problem. But for small numbers, like up to like 5, this is definitely perfectly reasonable. The peer-to-peer, this one is also, I think, for most of you, fairly familiar. So everybody is connected to everybody, including these cross connections here. So what is the advantage of a peer-to-peer system? Well, we have one sort of technical advantage and we have one conceptual advantage. So the first technical advantage is that we can use broadcast messaging. So we just send to everybody on the network and we have a single connection that lets us send to everyone. And this, while the first thing being that it is a technical advantage, that it allows you to work with one socket object on that level, it also is easy to combine with periodic sending. And just, this is my worldview and I am sending it to everybody who is willing to listen. It's a fairly easy combination. So data sharing, since data sharing is the whole point, is being able to broadcast your data to everybody is definitely a conceptual advantage as well as a technical advantage. But it also comes with its disadvantages, which is that everybody is sharing data with everyone. So back to that good old negation problem, how do you solve that? But another one is that there is no single obvious place to make decisions. So you're trying to make an assignment that one elevator should do one of the orders. The question is, who is responsible for making that decision? Because everybody has the data, and everybody is sharing the data, but is everybody sharing the responsibility to perform assignments? And how do you make sure that the solution that you get out is unique? Especially if your data between the nodes is inconsistent, you can end up in a situation where two nodes are trying to tell each other to take an order and everybody's refusing to do any work. And that is, shall we say, suboptimal. So for things where you need to do it in one place or you need to do it one time, a peer-to-peer system can be a harder thing to do than compared to a master-slave system. Because in a master-slave system, who makes the decisions? The master. Who distributes that data? The master. So in that sense, a master-slave system is better at the single source of truth stuff, but it is worse at distributing, because what happens if the master goes down? So they have kind of complementary advantages and disadvantages in that regard. Yes, and then the final one is a variant of the peer-to-peer system, which is a mesh network. And a mesh network, everybody is connected, but not necessarily directly. So this is an appropriate mesh network. Everybody is connected to each other, but not directly. And we can throw in a third connection here, but it might be unreliable, or it really doesn't matter. But something where not everybody is connected directly to everybody, but indirectly they're connected in some kind of graph. Now, what is the advantage of this? Well, you get the same things as peer-to-peer, right? The information propagation, if you do it, was just like, this is my worldview, and then you propagate it that way. The information propagation is pretty easy. So you get all the same advantages as peer-to-peer. It is, since you don't need direct connections to everybody, it is more robust to network interruptions and packet loss and so on. So it is even more robust, but again, disadvantages is going to have some as well. You need to explicitly encode trust of some kind. So we need to be able to say that not just, oh, this is what I know, but I know that someone you don't know about knows about the stuff. So you get this kind of indirect knowledge. So B doesn't know about what C knows, but B knows that A knows that C knows, and so therefore B knows that C knows. And that kind of indirect information propagation and be able to make that work is hard. And here's the hardest part, which is that the aliveness data, like who is alive? B never hears that C is alive, so how should B know that C is alive? Well, it needs to get that peer list from A. But in order to get that peer list from A needs to be able to remove C from the peer list that B knows about. So how is it going to do that? So now you're back to the list removal problem. So if you're able to solve the list removal problem when you are propagating the list as a trusted source with indirect list propagations, yeah, that might be a hard problem to solve. So yes, as I said, that may be a hard problem to solve. So for today's conclusion, I have included this final slide. Yes. Any questions?
Does it make sense for our project to consider mixing the topologies?
The question is, does it make sense for your project to consider mixing the topologies? Yes, it does. The question is, to what degree and in what way? So I think the things that it makes most sense for most people to do is to mix the master-slave idea and the peer-to-peer idea. So you have peer-to-peer to find out who is alive on the network. So everybody just broadcasts, I am alive, so that everybody knows who is there. And then you have some kind of master-slave idea to figure out who the data should be assigned to, or who the orders should be assigned to. And maybe you want some kind of peer-to-peer-like functionality to distribute that table so that in case the master goes down, somebody else can take over. Now the question is, do you actually mix topologies to do this? Or do you just mix the ideas from the different topologies and kind of fit one solution into a different topology? And I think the latter of those two, like you're trying to force fit distribution in a master-slave solution, or you're trying to force-fit assignment in a peer-to-peer solution. Those are the most common problems that need to be solved.